Hello everyone, and welcome back to the Shimadzu Introduction to Liquid Chromatography, Session 5. As always, our team are here to help. I'm sure you already know the LC team already, as well as some of our other technical staff, including the GC team and Jennifer Field, who guided us through the last webinar. Today's webinar will be presented by myself, Angela Jean. We have covered a lot of topics over the last 4 sessions, and today's webinar will be the concluding part of the Introduction to Liquid Chromatography series, where we'll use today's webinar to both recap on what we have learnt so far, as well as expand on some of the topics. This will allow us to create a firm foundation knowledge before we move on to the faster-paced sections of advances in liquid chromatography and method development. These will include topics such as UHPLC, building methods, and identifying errors within our data. So we will begin today's overview session. We have, over the course of the last 4 sessions, provided enough information for you to start to think about building your method. We would like to use the following 4 compounds to start to talk about how what we have learnt so far will allow us to develop a method, which we will then expand upon in our future series. Our first webinar started by looking at what chromatography was and used a paper chromatography example. The example showed the movement of the mobile phase across the paper, which allowed us to create a separation of our compounds into our final separated components. In this example, these were inks. We then created a list of the 4 main types of chromatography: paper, thin layer, gas and liquid chromatography, which we then concentrated on. We established a definition of what liquid chromatography was and what constituted the mobile and stationary phases. We also looked at the basics of how mixtures were separated within liquid chromatography. We then looked at the output, the chromatogram, and covered all relevant segments. The x-axis, which calculated the time the components were retained from, known as the retention time, the peaks representing our individual components, as well as the baseline and the base signal, and finally the peak areas used for calculations such as concentration. We also ensured that the types of compounds suitable for analysis of liquid chromatography were covered. We also checked which were not suitable. As mobile phase is a major constituent of liquid chromatography, we ensured that all the essential details were covered for the elements and properties that make up our mobile phase. We established that every solvent has a UV cutoff wavelength, at which analysis cannot be done below this wavelength. This is important when we get to building our method. If our compound has a wavelength maxima of 205 nanometers, we would not be able to use most of the solvents on this table. We would most likely use acetonitrile and water. If our compound's wavelength is 360 nanometers, however, then we are not restricted by our choice of solvents from this list. During the webinar series, we have looked at the LC column in a lot of detail. We started by establishing how the column was packed with particles, which had a honeycomb-like interior. This creates the web of pathways our components travel through. The compounds are attracted to the functional groups, which line the pathways and surfaces of the particles. These functional groups will feature more when we start to develop methods, what our choices are, and what we need to understand in order to choose correctly. We studied a representation of what is going on inside an LC column. The stationary phase is attached to silica particles and has a direction of flow for the mobile phase. If we inject a sample of these 3 analytes, they will start to move down the column, either interacting with the stationary phase or being carried along by the flow of the mobile phase. When we stopped the flow at a certain point, we saw that the 3 analytes were in different positions down the column. The red analyte, having had the least amount of interactions with the stationary phase, is ahead of the others. The green analyte has more interaction with the stationary phase, but less than the blue analyte, which has had the most interaction with the stationary phase and thus brings up the last place among these compounds. The chromatogram for this separation may look something similar to this, with the elution order of red, green and blue having the longest retention time. All mixtures are separated into their individual analytes by HPLC depending on their interactions with both the stationary and mobile phases. Our second session took this fundamental knowledge of how the column separates and looked at different types of separation. We looked at ion, size, normal and reversed phased separation. What types of interactions were involved in these different separations, as well as the basics of improving their separations. We looked at each of the types of chromatography in a little extra detail. Starting with ion exchange chromatography, we ensured we understood what types of columns were used. The separation exploited the natural repulsion and attraction of charges. The size of the charge and size of the attraction or repulsion will determine the time travelled through the column and thus the separation. Size exclusion chromatography uses a polymer or silica stationary phase. Separation is based on the hydrodynamic volume or size of the compounds. The larger the compound, the less the pores and pathways it can travel through, generating faster travel times through the column. Separation, as we can see, can then be further optimised after an initial screening process to alter the pore size and pathways in order to separate closely eluting peaks. Normal phase chromatography is the oldest type of liquid chromatography still used today. Using a mostly silica-based stationary phase, the technique has fully organic solvent mobile phases and polar stationary phases. Compound separation are directed by the polar affinities between compounds and stationary phase. Possibly the most commonly used type of liquid chromatography is the reversed phase. As an opposite to normal phase, non-polar ligands are attached to the silica base to create the stationary phase. In reversed phased chromatography, it has a non-polar stationary phase and a higher polarity mobile phase. It is still the interactions or rejection of polarity that create the separation. We looked at column chemistry in terms of liquid-liquid separation, which works in a very similar manner to our column. We showed that highly water-soluble compounds had a higher affinity to the aqueous layer, whereas fatty carbon-rich compounds had an affinity for the organic layer. We used these three compounds to illustrate the movement during liquid-liquid separation. We then looked at the partition coefficient equation that can help us predict elution of pure hydrophilic interactions. We converted our liquid-liquid example into column chemistry, replacing the fatty solvent layer with the stationary phase and the aqueous with a mobile phase. These can then be adapted for the other types of separation technique we have already spoken about. Let's not forget that even within reversed phase chromatography, different types of interactions are seen. We looked at the types of interactions we can expect between analytes and the stationary phase. In any separation, we almost never get a pure single mode of separation. In reversed phase, any separation can be dictated by a mixture of hydrophobic interactions, polar interactions, and ionic interactions. Hydrophobic is the major interaction. These are weak, transient interactions between a non-polar stationary phase and the analytes, and are typically predicted by log P values. Ionic interactions are between ionizable functional groups on analytes and countercharged species on the stationary phase. Ion exchange interactions are strong, slow interactions and can hugely affect peak shapes in reverse phase HPLC. Polar interactions are between polar functional groups of analytes and residual cyananols or polar groups on the surface of the column. Polar interactions include hydrogen bonding and dipole-dipole interactions. They are relatively weak and transient, but can significantly contribute to selectivity in reverse phase HPLC separations. Our journey would not be complete without mentioning the effects on separation. We just saw the interactions of the key ingredients in our compound separation. During our webinar series, we have looked at key elements such as solvent composition and how two analytes, reducing the strength of the mobile phase, that is, lowering the percentage of organic to water in our mobile phase, we can increase the separation between the two analytes. We also looked at the effect of pH. Depending on the pH of the mobile phase, analytes will be in either their charged or neutral state, which can affect both peak shape and retention. We also looked at temperature, showing the importance of keeping temperature consistent for good repeatability, and the increase in the temperature can aid our separation. We started today's session stating that we have given you information which allows you to start building a method. What can we start with? Well, our compounds have chemical properties. These can either be determined by research or experimentally. The maximum wavelength and partition coefficients are two such properties. From these, we can establish if our compounds can be seen with a UV detector. We can also start to predict elution order using the log P results. Having made some choices from our starting conditions, we can start preparing a separation. We can now look at the terms that we introduced in sessions 3 and 4 to improve this separation further. We will look more at what choices we have made and how we choose in further sessions. As part of our third webinar, we introduced a number of terms and concepts which should be understood in order to move effectively onto our wider topics. The two example chromatograms on the slide show a number of similarities as well as differences. What is the same between the two chromatograms is the retention time, and therefore the retention factor of each of the 4 peaks. We can also say that the selectivity is the same between the two chromatograms. Each peak elutes at the same order. What is different is the peak width, in this example measured at half the peak height. Because the width of the two peaks is different, but the retention time is the same, we can also say that the peak efficiency is different. Lastly is resolution, which is a measure of how well two peaks are clearly separated. This is also different between the two chromatograms. We first discussed the concept of void volume, and that we can derive this experimentally using various components such as water, which has no interaction with the stationary phase and can be used as a good marker for your void volume. In session 4, we established how the dispersion of the system is needed to understand the system in order to develop methods. We need to have our compounds suitably retained with good peak shape. Experimentally knowing the system with details such as dispersion and bandwidth of the peak will allow us to know what types of columns and particles we can use. Knowing the maximum pressure of our system is also essential. This will allow us to then choose the correct system parameters to have suitable retention using the correct column for our method. We looked at how we can calculate the retention factor and selectivity ratio from a chromatogram, allowing us to determine the validity of the methods we build. We looked at the efficiency of the peaks in terms of theoretical plates, allowing us to determine if the best possible column was being used for our separations. The higher the theoretical plates, the higher the efficiency of the peaks, within the limits of both the column and the instrument. One of the easiest ways to increase the efficiency is to reduce the size of the particles in our column. We can alter other dimensions such as length and diameter to maximise the efficiency of the compounds we are separating. When choosing the particle size, we also have the possibility of increasing efficiency using superficially porous particles. The introduction of superficially porous particles allowed development of UHPLC methods using lower pressure rated instruments. This practice is still used by many people today. In sessions 3 and 4, we looked at the Deemter Plot. Using the simplified equation, we studied how the 3 terms eddy diffusion, longitudinal diffusion, and resistance to mass transfer affected the overall performance of the columns. The resulting plot allowed us to determine the optimal flow of the column. Adjusting the column's dimensions altered the various terms. With the adjustment, we altered the overall plot and thus the optimal flow. So reducing particle size and plate height allows us to increase both the efficiency and optimal flow rate. Looking past the theoretical, for the experimentally observed vendetta of various columns, we combined the A, B and C terms to produce the curve of velocity. We can then see that the lower the particle size, the larger the optimal flow rate becomes. We also see that we can gain by using superficially porous particles. These are an asset if we are using mid-range pressure HPLC systems. Using systems of around 600 bar, we can begin to gain the efficiency of UHPLC methods without requiring the higher pressures. However, this does have a limit where we can gain no further. We looked at this by looking at two peaks with known retention times and peak widths. We then calculated the resolution between them using the equation shown on the slide. Note that this is the equation used for US pharmacopoeia, and other pharmacopoeias use different equations. Shown here are two peaks which are not baseline resolved, and they have a resolution of 0.8. Mathematically speaking, a resolution of 1.5 is considered enough for two peaks to be baseline resolved. However, in practice, a resolution of 1.7 to 1.8 is typically required. The equation for resolution, shown in the bottom right corner of the slide, demonstrates how efficiency, selectivity and retention all contribute. Selectivity has the largest influence on resolution at higher values. As we looked at in session 2, separation or selectivity can be changed by switching mobile phase, stationary phases, pH and temperature. Efficiency also has a large influence, but because of the square root doubling, the efficiency only increases the resolution by 1.4 times. As we have just seen, increasing efficiency involves minimising the effect of band broadening in our columns. Retention only has an influence on resolution at lower values. Ideally, the retention factor should be greater than 2 and less than 10. Beyond 10, it has no further influence on resolution. We looked at the beginning of this session building our method. The physical chemical properties researched or determined experimentally. But now we need to look at what questions we need to start asking to fully build our method, and what sections we need to think about. We start with our compounds. We need to establish what type of separation we would need to use in order to separate them. Would this be normal, size, ion or reversed phase chromatography? What stationary phase is then used, dependent on the type of separation and our compounds. What will our mobile phase consist of? Remembering that this is also determined by our column, type of separation, compounds, wavelength and various factors. Would we look at a static mobile phase composition, such as a 50% water, 50% organic solvent? This is known as isocratic. This remains the same composition throughout the whole analysis time. Or would we use gradient elution, where the percentages change with time? Do we need to optimise our column further by varying the column length, diameter or even particle size? What flow rate do we need to use? The optimal flow for the column can be determined. Do we require any additional reagents adding to our mobile phase or samples to create a suitable environment for separation, such as buffers? Do we need a specific type of instrument for our analysis, modular or integrated? Knowing that small particle sizes and shorter columns may optimise our method further, but do we have the instrument with suitable pressures, bandwidths and dispersion values that will allow us to create these methods? When we have all of these section answers, can we begin to predict the elution order of our compounds? And finally, what detectors are we going to use to produce our chromatogram? We will cover detectors within the Advances of Liquid Chromatography series. When we studied the list of questions in order to build our method, we looked at the type of instrument, whether it should be modular or integrated. A reminder here of the various sections being identical between modular and integrated. One of the key factors here is if two detectors or either a specialist item is needed for your analysis, in which case modular is a better system to go for. However, if it's a standard HPLC, both are acceptable for your instrumentation. Your choice then is dependent on your pressure rating. As part of building a method, we must choose the correct detector to prepare our chromatograms. If the detector cannot see our compounds, we can increase our development time or even stall it completely. There are many types of detectors and our choice is crucial, and we will take the time in a separate webinar to go over the various types. When we have our final choice of detector, mobile phase, column and instrument, we will start to develop the best method. How do we make the best method? What do we do if the chromatogram changes over time? These sorts of issues will be covered in our further sessions in order to create the best method and optimise it. Lastly is an example of what we can do with our new knowledge. The two chromatograms look fairly similar. They've been run isochromatically, meaning the mobile phase composition remained constant throughout the run. The resolution between the first two peaks is almost the same, and the plate count or efficiency of the large peak here is very close. But the difference is the runtime. The top chromatogram was run in 35 minutes and the bottom in just 4. So in changing the column and the conditions, we have created an optimised method. However, we have now increased the pressure. So will our instrument be sufficient, or do we need to start looking at using UHPLC? If you want to know more about your choices, join us for the Advances of Liquid Chromatography course that will start looking at UHPLC. This now completes the Introduction to Liquid Chromatography series. We hope that you've enjoyed this series and will join us for the Advances in Liquid Chromatography series, which will start in September and will cover topics of UHPLC, detectors and software features. Please visit our website www.shimadzu.co.uk/webinars for other webinar series that are open for registration as well as available on demand. This allows you to look at some of our past webinars if you have missed any of the other sessions. If you'd like to hear more from Shimadzu, please do join our mailing list. You will receive all the news and product development from us. Look for the link on the follow-up email or go to our website and click on e-news located at the top of the screen. You can find us on all the usual social media platforms, as I'm sure you are aware. Please feel free to contact us should you have any questions or wish to find out more. That's all from me today and the completion of this series. We look forward to hear from you soon and hope that you join us for our next series starting soon. Enjoy the rest of your day and take care.
Excellence in science. Shimadzu.